Thanks so much for inviting me. I'm going to talk about this. So I'm going to really just talk about two themes which are quite different. And following in the general science norm, I'm not going to talk about a particular paper. I'm going to give you a kind of whirlwind tour of two themes. One is, when do we expect Nash equilibrium to predict behavior well in the lab, and also a little bit, I'll show you a little bit of field data. And the second thing is pretty orthogonal, which is I want to introduce you to a distinction that's become very important in cognitive neuroscience, and as well as in CS and many other fields. It started really in animal learning, and kind of advertised it as something we might think about more in game theory, which is called model-free versus model-based theories of choice. Okay, so let me start out by talking about what I think a good model should do. It should fit lab and field data. The lab, remember, is really just a way to hone and control theories to then hope that they can predict things like RICO racketeering and chimpanzees playing games in the wild. Ideally, if there's a free parameters like there are in these theories and level K type theories, they should be somewhat predictable. That doesn't mean it has to be a universal constant, but it means you should have a kind of guess about a new game, what a parameter value might be, or you should be able to estimate that. I'll say a lot today about when an equilibrium concept like Nash is likely to be wrong or right. It's helpful if a theory, an alternative theory like level K or noisy introspection or analogy-based equilibrium is also tractable for doing theory. That often distinguishes the way psychologists think of things, which is if you can predict, but it has a lot of moving parts, then that's useful, but it's not useful typically for doing theory. And finally, this is not obviously the norm in economics and a lot of allied fields, is that we can often find a lot of theories that have these properties. Like even for bounded rationality, there's a bunch of theories I mentioned, but some of them may just not be what the brain is actually doing, and I care about that. I care about that. And because economics as a field, and I think game theory to some extent, even though I understand this, they don't perfectly overlap, is actually pretty good at coming up with a new theory, right? So there's the Ellsberg paradox and a lot of associated data about ambiguity aversion, and there's dozens. If you take the country of Italy alone, the country of Italy has produced dozens of theories about ambiguity aversion, and they're not all going to be what the brain is doing. So one way to winnow down theories is to collect other types of data. Okay, so when does Nash equilibrium predict behavior well? And I think there's basically three answers, and I'm just going to give you like a taste of each of these, not an authoritative review. Well, actually, I think it is it's my view, but I'm not going to give you a big review with dozens and dozens of papers. One is after learning. So despite the kind of flimsy underpinnings, as I understand, like Sergio talked about, generally when players in the lab or in a field data, like I'll show you, play over and over, they do tend to converge to Nash equilibrium. Okay, I think there's some evidence that when people play in teams, that tends to promote convergence to Nash, but I don't know much about that, so that's why I put it in gray. And I think the most interesting thought is when games have strategic substitutes, you tend to get convergence. When there's strategic complements, you tend to not get convergence. And here, by convergence, I mean even in one-shot games where there's no learning process. I'll show you some examples. What seems to not matter, perhaps contrary to your intuition, is subject populations. So I'm going to show you some data from lots of students, from New York Times readers, and from Nobel Prize winners in game theory. And they're not very different. Stakes also don't make very much difference. If you increase the stakes a lot, like 5 times as much money in a lab experiment, you might get like a little extra half a step of convergence to equilibrium, and where a step is on a level K scale. Okay. And I'll since I teased this, I'll tell you what this is, but I don't have time to show you. The exception is chimpanzees. So we have a paper with chimpanzees in Nagoya, and using touchscreens, they play a hide-or-seeker game. They're extremely close to Nash equilibrium. Basically, when the equilibrium is 0.75, they're 0.01 off. It's really eerie. Okay. Okay, so first example of complements. This is a Swedish lottery that was actually played for 7 weeks in Sweden. Robert Oschling came and visited us. Thank you, Robert. And he and Joseph Wang at NTU in Taiwan did some math that I can't do, and you'll see the fruits of their labor in a minute. So in this lottery, people choose integers from 1 to 99,999. That constraint is because they use these cards to fill them out, so there's a natural physical constraint, right? And the game is very simple conceptually. The lowest unique number wins a big prize, which is 10,000 euros. So this is a really nice mixed motive kind of game in the sense that you have to pick low. That's easy, right? Lowness is a very simple property, right? But you have to be unique. That's hard because everyone wants to be unique, right? And you'll see what the equilibrium is going to look like in a minute. Thank you to Roger Myerson because we use his theory of Poisson games. Okay, so what might happen? So in the Poisson-Nash equilibrium, if the number of players is Poisson distributed, right? Actually, if the number of players is fixed and known, it's computationally intractable. So this is a quirky case in which having uncertainty about the number of players actually simplifies things, if it's Poisson. There's a lot of magic in Poisson games. And so if the number of players n is Poisson distributed, then the frequencies P of k of choosing integer k, this is in a symmetric mixed equilibrium, satisfies this system of inequalities. This is slightly wrong. There's 99,998, and there's this many unknowns, but they add up to 1, and so you can actually solve this. And when you do, it looks like this. Okay, so the numbers from 0 to 5,000 should be chosen almost equally often. Almost equally often. So 1 should be chosen the most often, 2 slightly less often, so there is a lowness bias, but it's very, very flat. And then amazingly, it plunges at around 5,518. And that is just game theory magic, right? It's Poisson, there's a mean number of players, there's a range of numbers that are picked, that's it. And boom, you get this beautiful, highly unintuitive curve. I mean, to me, it was highly intuitive. Let's see if subjects play this way. So in the first week, this is 350,000 observations. If you plot all of them from 0 to 100,000, this is the Poisson-Nash equilibrium. It's on a different scale, because the one I showed you before is only up to 10,000, right? This is up to 100. This is the equilibrium. Here's the data. That is pretty good. That is pretty good. It's not quite right. I mean, it's off in 2 ways, but it's amazingly close. For example, if I had given you the data or given my Caltech students the data and said, think of a theory that might fit these data, I don't think it would have done much better other than some empirical curve fitting. That's what they would have done, by the way. All right? So if we chop off the lowest 10,000 and take a look, here's what it looks like. So there's way too many people picking low numbers, like up to 1,000, like 1. A lot of people are picking 1, 2, 3, 4, 5. And again, this is not the dumbest thing, is it actually should be the most common number picked. It's just that too many people are picking 1. What they're thinking is, low and unique. I'm going to pick 1. Like, no one is going to think of that, right? And of course, everyone has the same idea. Okay, but because there's too many low numbers, there's a gap between 2,500 and 5,000. There's missing data there. And it doesn't quite show this sharp drop, right? You should see no data above 5,518, and there's some. It's about 8% of the numbers are above 5,518. But that's pretty good. There's a
What's the total number of participants?
53,000 each day.
Each day?
Each day, yeah. So this is 1 week, which is...
That came from some restriction?
No, that's just how many people...
So that's really not a Poisson distributed.
That's the mean of the Poisson.
Each day?
Yeah.
There is a prize?
Each day.
Each day the same number of people participated, or that's 53,000 is the average?
The average, yes. Yeah. And by the way, the participant distribution does not fit Poisson particularly well. So this is a case where, as is often true in economics, we make an assumption that we know is wrong and see if it turns out to predict okay.
How much does it cost? 1 million.
Sorry?
How much does it cost?
€1.
How many chances there were?
1 to 99,999.
6 digits.
Yes.
Okay.
Yeah.
So it is a million now. So it's 5 digits. I thought
Oh, 5 digits, yeah.
you showed the 6.
Yeah. What?
6 cards. Oh, okay.
Oh, yeah. Oh, the 6 cards just means if you want, you can buy 6 numbers on one card. Yeah. Okay. All right. So basically, there's too much data here, too many choices here, not enough choices here. If we fit a model called cognitive hierarchy, and we fit a level K model too, there's just slightly variant, I'll explain in a minute, you can actually get a pretty good fit. This is a 2-parameter model. It has a quantum response softmax piece, and tau is going to be the mean number of levels of thinking in a hierarchical level K model. It turns out to be 1.8, which is amazingly close to what you often see in lab experiments and other data. And what tau does is it basically explains all these low numbers by people who are doing low levels of strategic thinking. They're not thinking enough about uniqueness and what others do. Okay, and so by fitting this part of the distribution, it underfits here. I mean, it underfits the equilibrium, but that's where the data are. Okay. So Reinhard Zelten, a long time ago, said the natural way of looking at games is not based on fixed points or circular concepts, he calls it, but rather on a step-by-step reasoning procedure. And he had several papers sort of discussing this. Okay, so the way these cognitive hierarchy level K theories work is, this is not a theoretically conclusive thing, it's just enough to get in your mind, is that there's some 0-step players who choose what I now think is something salient, and if there's nothing particularly salient, they choose randomly. Randomly is often a good starting point for various reasons. The 1-step thinkers think others are 0. 2-step thinkers either think others are 0 and 1, that's in the specification we call cognitive hierarchy, or level K, the 2-step think that they're playing 1-steps. And they know the 1-steps are playing the 0s. Okay, and these are empirical. Vince has worked on a lot of these, Vince Crawford, and these are empirically, very close kind of family relatives. So,
2011 should be a 2013.
Oh, it should be 2013, okay, yeah. So this is an extremely thorough, this is our early paper, this is an extremely thorough review, 2013, in Journal of Economic Literature. So an important question is, what's the percentage of people at different levels? So one theoretical guess is if you assume the fraction that are doing K level thinking rather than K minus 1, kind of like a graduation rate, right, graduating one more level, is proportional to 1 over K, then that axiomatically implies a Poisson distribution, and you can see here. For example, for Poisson parameter of 1.5, there are a lot of level 0s, probably more than is realistic. Vince and I have been debating this. The max is about 1/3 who are at level 1. There are quite a few at level 2. And the nice thing about Poisson, because of the K factorial, is that it drops off very, very quickly. So we basically, in estimation, we barely ever look for level 5s and level 6s. We just don't think they exist in these domains. Okay. All right, here's a GIF made by Robert. Here's what happens over all 49 days. After 49 days, they just stop the lottery. So this is a fun thing to teach, by the way, because it's very rare that you can show your students a graph like this. So somebody says, what happens if you play over and over for like a few weeks? This is an answer to this game. So yeah, I'll come back to that. So the low numbers disappear gradually. They quit playing 1, right? This starts to get filled in, but only a little bit by the time they get to 49, right? Remember, it started out with this gap here, a big gap. It gets filled in. And as Vince Crawford pointed out, what's the deal with 2000? It's lucky numbers. So if you look, there's a graph in the paper. If you look at this very carefully, there's a lot of people we think it's birth years or birth years of children, right? So there's a lot of 2000s being picked. Think of those as a level 0 who's choosing on the basis of personal salience, right? And interestingly, there's anti-focality too. So it turns out there are a lot of people don't pick 1970, they pick 69 and 71. So there's some strategic thought, right, that 1970 is a round number, I'll avoid that. But because people avoid it, it's actually better to pick. Quick question?
What feedback did the participants have?
There's a TV show that you can watch that tells them, it actually starts at the top and goes down to all numbers, and it pauses when he gets to a unique one. And then at the end, you see, like, the unique one might be 2,412.
So they see every day.
If they watch the
winner, what was the winner?
Correct.
How did the winner look? Do you have a graph of that? That would be interesting.
It's, the winners are, start out around 1,900 and it moves up to 2,700 or something like that. There's a table in the paper, I'm gonna have to move on, sorry. There's a table in the paper that lists what happens in the first week, what happens in the last week, and the equilibrium predictions. And every statistic except one moves toward the equilibrium. Median, mean, interquartile range, percentage of round numbers like tens and hundreds. It's really striking. It's across the board. Every feature of the distribution is moving in the right direction over 49 days. Okay, so we did a very unusual thing. We went field to lab. So because the field data was so carefully pinned down, we could do the same thing in an experiment, and then we could do other things. Like Sergio says, we could make sure they get certain kinds of feedback. Like we could tell them the winner, we could tell them the whole distribution, we can control the feedback. The other thing we could do is we can look for our individuals mixing across their trials. In the field data, we don't know that. We just know the aggregate distributions. And so we did this at UCLA. The first 7 trials, or days, right, this is what the data look like. And this is a scaled down game. It's not 99,000. They pick numbers 1 to 99, and there's 26 of them that play. And when you compute the equilibrium for that, the Poisson-Nash equilibrium, it looks like this. It's almost a straight line that ends at 14. Remember, they can go up to 99. So there's a very bold prediction, which is that only the lowest 14 numbers, 14% of the range, should be picked. That's a really bold, strong prediction. And it should have this, slight drop-off.
The fact that you have 26 people, that if you have 260, it will be very different.
Correct, exactly. Yeah, yeah. I mean, so you can control the number of players, whether it's Poisson or fixed, and the range of integers, and anything you else want to do. That's right. It's not too late to do lab experiments. Okay, anyway, so I think the fit here is really good. This is after 7 trials. It slightly reproduces the data, which is a little bit too many low numbers, like too many ones, but only by a small amount, and then a little bit of a gap here. And then you see hardly any high numbers. Okay.
Did you always get a unique lowest number?
Yes.
26 out of 99.
Yeah, this is the mixture.
Oh, I'll say 1. Oh,
Yeah.
Sorry.
Yes, yes, I think we haven't proved any general theorems, but I'm pretty sure in general it's going to have this structure, that there's some flatness, then it goes down. In the large case. In the smaller case, you don't really see flatness and then a plunge, right? You just see a slighter gradation. Okay, so at a 2021 conference in Sweden, we actually played this. Some of you might remember. And there were 4 Nobel laureates at least. I may be off on the count. Anyway, so the data is very noisy. I combined that data with data from my class, right? And so the data are very noisy. Here's the equilibrium, right? The Poisson-Nash equilibrium. And this is the blue is the smooth, kernel smooth version of the noisy data. And so this does not particularly look like the other data, right? Here, there's not enough people picking low numbers and too many high numbers here. And about 27% of the people picked above 14, right? So this is an example of robustness to subject pool. I was so happy I had this chance. Thank you for everyone who participated if you were there. And because now people often say things like, well, if you had some really good game theorists, we did. And ironically, Daron Acemoglu won by picking 2, right? And I guess that's enough to get you a Nobel Prize, right?
Minus than I think 4, what could we do? I mean, 2 wouldn't be either, right?
Yeah, I mean, again, it's noisy, right? So 2 is not the equilibrium says you should get a lot of 1s and 2s, right? And he happened to pick a 2, and he kind of got lucky that nobody else picked 2, right?
How many people you have here?
I think it was 41 in the conference, and then the Caltech student classes were maybe 30 or 40.
So they all competed on the same prize?
Yes, yeah. So there's two,
So what, 70 people? 70 people?
I can't remember. 26. Yeah, the total is 126. Okay, let me move on.
126, and there are 100 numbers possible, or 99 numbers possible, right? So it's more than, on average, it's, because that matters.
Yes,
How many you expect on each number?
So in both cases, what I told them was, we're going to choose from a Poisson distribution a number of players to be active.
Tell people Poisson distribution, who knows what?
To be active.
You think you understand that?
Well, Eric Maskin was there. Paul Milgram was there. I think Paul Milgram could probably figure it out. Okay. All right, another example, strategic substitution. In congestion entry games, Liat introduced some ideas here. So this are games in which there's n entrants. Again, I'm going to show you empirical data from, I think, 20 entrants, potential entrants. There's an announced capacity C, right? And the payoffs are very easy. They either enter or not. We'll call 1 or 0. If they stay out, they get 1. If they enter, they get 2 if the capacity or fewer enters. And if too many enter, more than the capacity, they get 0. Okay, so entering is kind of gambling on 2 or 0, depending on whether you think the right number of people will enter. And there's tons and tons of Nash equilibria, right? Imagine we played this game sequentially, right? If we played it sequentially, what would happen is, let's say we have 20 people. We go around the room. The first person says, I'm in, second person in, there's 8 in, and the capacity is 8. 20 people, capacity of 8. The first 8 people say, I'm in, everyone else says they're out. Right, so sequentially, you can kind of implement an equilibrium. They didn't play sequentially. They're going to play it simultaneously. So how do they decide which 8 people get to win 2? No communication, no communication. So here's a simple model. This is a cognitive hierarchy type model. Level K will work kind of similarly. So let's say the level zeros just enter randomly independent of capacity. They just don't even think about it. Okay, again, you could put a different assumption is, but that's mine. Yeah, you could have lucky numbers, you could have something else. This case is nice for a reason. So if the level zeros enter randomly, that means 50% of the time they'll enter independent of capacity, right? The level ones will work against them, right? So if the capacity is low, below a half, then they know the level zeros have flooded the market, they'll stay out. So this is the best response to perceived level 0 play, all right? Good, nodding. Now, if you average these together, the averaging depends upon the percentages, right? So in Poisson is a particular one, but there's other ways to do it. If you average it, it's starting to move a little closer to the equilibrium, which is here, right? This is level 0 and level 1. Now, level 2s, if they think they're playing 0s and 1s, right, what happens is they have this complicated structure. They stay out here because there's too many people entering at low C. They're out, they're in, they're out, they're in. What they're doing is they're filling in the gap between the conditional entry rate and the equilibrium, right? And so if you add 0s and 1s and 2s together, you get a step function that's deterministic. You could put softmax in. I don't think it's going to make much difference here. You get a step function, and the 0, 1, 2 step function is starting to close in, right? And in fact, so we call this kind of like pseudo-sequentiality or mentalized sequentiality. The higher level players are kind of acting like they're going after the lower level players. They're not. They're all thinking simultaneously. But the hierarchy is akin to an actual sequential play. Right, that's the idea. I'm glad Sergio's nodding. Okay, and so here's some data. So this is the experimental data in pink, right? You can say they over-enter here and they under-enter here. And if you fit the cognitive hierarchy model with tau 1.25, it looks pretty good. It's got the basic features. It's monotonic, right? Here it's strictly monotonic. The data's not quite there's a small miss here, just a sampling error dip, right? It's got the two main features. It goes up. It's not too far from the dotted line, which is entry equals demand, Nash equilibrium. And it overshoots here and undershoots here. Okay, why is this interesting? Partly because one person wrote in 1988, observing the regularity behavior in these markets was a bewildering experience. To a psychologist, it looked almost like magic. And that is Danny Kahneman, because he had done some experiments with Jim Brander, who's a trade theorist, and Dick Thaler, who was visiting, and I think they kind of gave up because they kept getting entry rates that were kind of like the equilibrium. And I think Danny was not interested in bias and mistakes, right? And so hence this thing, almost like magic. And it is like magic because we think because of this levels of reasoning, the pseudo-sequentiality kind of gets you there with no communication and no experience.
By the way, you're treating the diagonal line as the Nash equilibrium.
Correct.
Function. I would argue that the relevant one is the symmetric mixed strategy.
Correct, correct.
And the real magic is that they do better on average than they do in the best symmetric Nash equilibrium. So
The symmetric mixture.
the symmetric
Yeah. The symmetric mixture is pretty close, but we talk about it in the paper. But it's not exactly, yeah. That line is for if you could somehow implement the efficient asymmetric pure equilibria, where 8 people somehow, C out of n figure out how to go in.
So connected to that, can your data show whether it's the same group of people that are always in?
Oh, yeah,
which
yeah.
means that the level 4 or level 3,
Yeah.
whoever, they are really the level 3. It's not that once they are in level 3, once they are in level 1. Can your data show that?
Our data, we just did it one shot because we wanted to see what happens in one shot, I think. Amnon Rappaport and a bunch of others have studied these games too. And the general answer to the question is, are people a fixed type over and over? Some have found pretty strong correlations, including Vince, and some have found that in different games, people switch types a lot. So that's the state of the art on that. Okay. All right. So the answer to the question of when is Nash equilibrium close to or far from behavior, at least a partial answer, again, this is not a theory, these are just observations from data, is that when there's strategic substitutes, right, like in the loopy game, right, if you pick a number, I want to pick a different number. In the entry game, if you over-enter, I want to under-enter, right? So that seems to be a recipe to get good quality approximate equilibration even the first week you play loopy or the first time you play these entry games. Another example that probably I hope a lot of you are familiar with, because I'm not going to have to go over it much time, this is a 2/3 of the average game. Everyone picks 0 to 100, closer to 2/3 of the average wins. And this is a lot of people. It's 51,000 writing into the New York Times, picking a number. Okay, so this is, again, a pretty elite readers of the New York Times. And so when I type my guess of 20 in, it's here in red, right? At that point in the game, the average of all the guesses was 28, and the winner was 19. So it was just 1 point off, right? And again, and what you see here is there's a lot of people picking 50, right? A lot of people picking 33, which is 2/3 of 50. People picking 22, which is 2/3 of, right, 33. And then there's kind of a gap, right? And there's a lot of people picking 0 and 1, which is too low. I mean, it's great if you're trying to answer an exam, like what's the Nash equilibrium at 0. If you're trying to impress readers of the New York Times or win money, you're too clever by half, as the British say. Okay? So this is an example where there's strategic complements, right? The Nash equilibrium is 0. If you choose a number much higher, I want to choose higher too. So the complementarity drives people away. And by the way, this idea, Waldman and Halterwanger, quite a long time ago, wrote about this importance of complementarity as a sort of recipe for how small irrationalities might get magnified. You can think about price bubbles and other cases like that, right? If there's a few traders trading very erratically, everyone else may want to trade erratically, kind of like some other, like Rachel and others were talking about before. Let me skip this one for time. Okay, second thing, model-based and model-free. So the way we use this in cognitive neuroscience is model-free uses only data on experienced state action reward outcomes. So if you haven't done it and collected a reward, you have no idea. You could put in some kind of prior or some kind of subjective belief. That's called model-free. And again, this comes from animal learning. Model-based means there's some kind of model. It could be a decision tree, right? It could be something somebody told you. It could be something you read in a book that predicts rewards from any state action pair using either instruction, observational learning, blah, blah, blah. And that means you can choose well among novel state actions. Like if there's actions you've never picked, right? Like the number 3,142 in the loopy game, if you have a model, you can compute an expected value of using that. Okay, so here's an example. When I came out here, I took a ride with Leslie, right? And what I learned was it cost $84 and it took an hour and a minute. So those are what we call reward in cognitive neuroscience, right? And I learned about one trip, right? I learned Leslie from Lyft cost me this much time, money and this much time. And other trips, like this trip to Manhattan Beach, you type in your destination, and this is model-based. So I've never been to Manhattan Beach, but what this tells me is, if it was a Lyft, it would tell me the price. But this is me driving. It just tells me the price in terms of time. So this is model-based, meaning it enables me to compute the likely reward from any action that I've never taken before. Okay. All right, there's a precursor to this. So we talked yesterday about Nash's mass action idea. And the key phrase here is the participants are supposed to accumulate empirical information on the relative advantages of the various pure strategies. Accumulate empirical information, like play, do it or play it, right? In this paper of Jorgen's, in the footnote, they kind of extend that to something they call innovativeness and inventiveness. And the idea is that the present formalization presumes that the individuals playing the game perceive the payoffs even to those pure strategies that are not in use, right? Like this. Okay, and so this is model-based and free and model-based. They didn't use those terms because they weren't in vogue and they really came from elsewhere, but it's the same basic idea. Okay, why do we believe strongly in this? Because it's in the brain. So if you do experiments with rodents in ventromedial prefrontal cortex and these dorsolateral and dorsomedial striatum, it turns out that these brain regions account for these model-free, model-based behaviors. How do we know? If you lesion this in a rodent, they quit using model-free habits. And we can't lesion humans, at least, I mean, nature can do it, but we can't. But it turns out if you do human experiments with fMRI, you get homologs of these same areas when people are behaving habitually in a model-free way or not. Okay. And finally, another place model-free, model-based shows up is reinforcement learning is model-free, fictitious play is model-based. We had this paper a few years ago that kind of hybridizes these. Basically, this says if this is a strategy you did not play, you multiply a weight delta times the foregone payoff, which you can compute because we give them a matrix. And so delta is kind of the degree of model-basedness. One more informative slide. This is work by my academic granddaughter, Lucia Zhu and Ming Su. And so they played a particular stylized patent game. And the way these neuroscience studies work is you take behavior and you fit a model. And then that will give you a set of regressors, which is the belief-based expected value of a strategy. And then you correlate that regressor, which is going to change trial by trial by trial, and you ask what parts of the brain have activation, which looks like the activation that looks like that pattern of numbers. Okay, when you do that, and you look for the hybrid model, the EWA, it turns out in this region called rostral anterior cingulate cortex, there's no reinforcement learning signal, and there's a belief-based signal. And furthermore, across subjects, the estimated value of delta, that's the weight on fictitious play, is strongly correlated with activity in this across people. So these people with high activity have high deltas. Okay, so this is a reason why we think that this EWA makes sense, because it's in the brain. Reinforcement learning does not make sense because it excludes a belief-based component, and the brain is computing belief-based. And this just makes the same point. So here's my visual conclusion slide. 7 words and 3 pictures. When does Nash equilibrium predict pretty well? When there's strategic substitutes. If there's strategic substitutes, yes. If there's complements, no. We can be quite far off from Nash the first time they play or the first few times. Learning does, by the way, in these games, they learn to gradually get to 0 pretty quickly, 5 or 6 tries. And I also illustrate a model-free and model-based as a fundamental distinction. It goes back to Nash and then Jorgenweibel, and is also evident in the brain here in an empirical game played in the brain scanning. Thank you. Sergio.
Your substitutes and complements look very much like stable and unstable Nash equilibria. In one case, when you move away, it leads everybody to move away. That's the unstable case.
Yeah.
The stable one, when you move away,
Right.
everybody moves back.
Yeah,
And
yes,
that's
correct. Yeah, yeah.
Parallel distinction, I think.
Yeah, maybe that Ernst Fair and I published a paper with this distinction in it, and neither of us are game theorists, but it maybe there's some, this is not the end of the story about a fundamental distinction.
First of all.
Oh, yes.
Serious question, like no jokes. With these lab, distributions, like picking lowest number, with those 2/3, 200s, 2000s.
Correct.
Can you derive gender? Like, can you separate men and women results? Well, you can make an experiment similar to those 90, 100, 200 people.
Yeah,
Right?
I don't think.
That would be my suggestion.
Yeah, I'd like to know the answer. I think that, to be honest, the gender effects in experimental economics are pretty mixed, even where you might think, for example, you might think women are more pro-social and cooperative, but in Prisoner's Dilemma, they don't cooperate more. But it may be because they think other people won't cooperate.
Lucky numbers.
Oh yeah, it could be lucky numberness works differently, yeah.
I have K. I have level of K. Is there a difference in that?
Yeah.
That's an issue.
We do have some data from a price bubble experiment, and the men, this is called the extreme male hypothesis, the men lose more money and win more money. So they're more likely to participate in the bubble and get lucky, and also, and so women are just more cautious traders. And there is a bunch of evidence on female aversion to financial risk, and women don't participate in the stock market in quite the same extent. So there are domains, where gender works in a way that you might expect.
So in the games that you presented, you have quite a small number of options that you can choose, right? But in the real life, to make a decision, you might have to make several sub-decisions. So suppose you could have a decision or a strategy is a bit string of length n. In that case, do you think the Nash equilibrium is a good model of what humans would do?
Give me an example game again, like
So
with a large strategy space.
let's say we just take, so a bilinear game, like a very simple game. You just count the number of 1 bits, and then you have some bilinear function on that. Do you think Nash would correspond to what humans would do? Because in this case, you can't really imagine all the possible solutions you have.
I don't know. I'm not digesting your question very well. There are experiments and data with lots of strategies, so I don't think that necessarily handicaps things. Like there's data on coordination games with 100 strategies, so on. Vince?
My 2006 AER paper with Costa Gomez.
Oh, right.
Huge strategy
Yeah.
spaces.
A large range of numbers.
And there's definitely not a lot of support for equilibrium. There's some, but actually we think those subjects are just doing something that's a rule that mimics equilibrium in some of the games, but not all of the games. But the more precisely you see how people are thinking, the less you're going to like equilibrium in initial responses to games, I would say. And we also don't find any significant gender effects in that.
Oh, okay.
We should end it there. Colin, I think that
Yeah.
we should end it there. Thank you very much.